Okay, so here, this is all in the context of related rates, right? We're going to deal with just cones here, right? As a dimension of the cone changes, how will that change the volume of the entire cone, right? We want to see what does the change in the volume depend upon is ultimately what we're looking for. Now, there's two different ways. So what's going to happen here is we're going to increase the height. The cones are going to get taller. And we have to consider the implications of this, the consequences of increasing the height of a cone, right? Two ways. We could hold the radius constant and just increase the height, which means that as the cone gets taller, it would get narrower because the base of the cone, the circle, has to stay the same size. So it looks something like this. But what if we wanted to maintain proportionality, that as our cone increases, the big cone that it is now is proportionally the same. It is similar to the size it was when it started to increase. What we notice here is that implies that the radius will change. And that's what I mean by changing radius here, is the radius is only changing because it's forced to. If you want to maintain proportionality, that radius will have to change depending upon the height. Now, I'm not giving the radius its own expansion here. It's not going to increase on its own free, independent will. It is completely bound to the height, right? So let's see what the formulas would be for these. Well, start with the volume. Volume is 1/3 pi r squared h. And again here for the first one, we're holding the radius constant, which means the only function here, the only variable is the height. So v prime, or dv dt, the derivative of the volume with respect to time, would be pi over 3 r squared h prime. And that's it. R squared is a constant, so we would not change that. Good. Now, over here, though, we want to maintain proportionality. So the radius will change, which means the radius is a variable, which means when we take the derivative of it, we would have to use the product rule because r squared and h are both functions of time. But what if this was avoidable? What if we were told that the radius and the height, they do relate to each other. So maybe the radius is a times the height. Some constant of proportionality here would be a. Maybe it's twice the height. Maybe it's only half the height or a third of the height. And we can make the substitution, because if the radius depends upon the height, then we could do the volume in terms of just the height. So that would become pi over 3 a h squared h, or pi over 3 a squared h cubed. So now you have the volume strictly in terms of the height, which means the change in the volume would be pi a squared over 3 times 3h squared times h prime. So what you'll notice here is the change in the volume here doesn't actually depend upon the height. It just depends upon the change in the height. Here you need to know the height at the given instance that you're looking at, and the rate of change of the height at that instance as well. So this is definitely a little more intricate. But yeah, it's just, what do you want? Do you want to hold the radius constant, or do you want that your bigger cone is proportionally the same as the smaller cone? And these would be the respective formulas.